Hello everyone, this is Mahdi Amina. Today I am presenting my research titled AI powered personalized therapy for children with autism, a reinforcement learning approach. First of all, introduction. Autism spectrum disorder or ASD affects roughly 1 in 31 children worldwide, a figure that continues to rise due to improved screening and awareness. Despite this progress, many children still face a lack of individualized therapy as traditional one size fits all approaches fail to address the wide variability in symptoms and needs. This presentation introduces a novel AI powered approach that aims to personalize autism therapy through reinforcement learning. The study integrates behavioral data with advanced deep learning models to enhance early detection and create adaptive treatment pathways by combining data driven insights with clinical expertise. This project seeks to revolutionize how therapists tailor interventions to each child's unique developmental profile. The overarching goal is to demonstrate how artificial intelligence can help clinicians make more precise, dynamic, and child specific therapy decisions. Then I'm going to talk about the research gap. Current research on autism intervention heavily emphasizes a static diagnostic classification rather than ongoing therapy adaptation. Most models can identify whether a child is likely to have ASD but cannot adjust treatments over time based on behavioral changes. Reinforcement learning, which has proven successful in other areas of medicine, such as intensive care, remains underutilized in autism care. The absence of dynamic, feedback driven therapy models represents a significant gap. Moreover, existing approaches often neglect interpretability, making clinical application difficult. This study recognizes that addressing this gap could transform autism therapy into a continuous learning process that evolves with each session. By leveraging validated screening tools like the AQ10 and embedding adaptive decision making capabilities, our research moves beyond detection toward genuinely personalized, evolving therapy recommendations. Then I'm going to talk about the research objectives. This study aims to build a comprehensive framework that integrates machine learning and reinforcement learning principles for autism therapy personalization. The first objective is to develop robust deep learning models capable of accurately identifying ASD using behavioral screening data. Secondly, the study design a reinforcement learning inspired architecture that recommends adaptive therapy actions responding to ongoing child progress. Thirdly, we compare two major AI models, a DQN inspired neural network and a transformer architecture, to assess performance, stability, and interpretability. Finally, we identify which behavioral and demographic factors most influence the model's decisions, offering actionable insights for clinicians. Collectively, these objectives ensure that the study not only improves screening precision but also contributes to a more dynamic, responsive, and ethical model of therapy planning that learns and evolves alongside each child. Then, about related work. Artificial intelligence has already transformed healthcare by optimizing decision making processor. For example, the work by Komorowski and colleagues in 2018 used reinforcement learning to enhance sepsis treatment strategies, showing that machine learning can outperform human judgment in critical care. Similarly, Liu and colleagues in 2020 demonstrated reinforcement learning's effectiveness in ICU drug dosing and intervention scheduling, within Autism Research Co. et al. In 2023 developed a deep learning model achieving over 99% accuracy in detecting autism through joint attention behavior, while Raja Gopalan et al. In 2024 applied XGBoost to large datasets with promising but less generalizable results. Despite these success, most models remain static and non-adaptive, lacking real-time personalization and interpretability. This research bridges the gap by combining deep learning precision with reinforcement learning adaptability, aiming to build a framework capable of evolving with patient feedback for continuous therapeutic optimization. Then I'm going to talk about dataset and preprocessing. This study uses the Autistic Spectrum Disorder screening data for adults, a publicly available dataset consisting of 704 records. Around 27% of participants fall within the ASD range, while 73% represent control cases reflecting realistic class imbalance. The dataset includes validated AQ10 behavioral questionnaire responses along with demographic information. Data preprocessing involved median imputation for missing values, label encoding for categorical variables, and standard scaling to maintain numerical consistency. A stratified train validation test split preserved class ratios to ensure fair model evaluation. This structured approach minimizes bias, prevents overfitting, and strengthens the reliability of model outcomes by maintaining the natural imbalance rather than artificially oversampling. The dataset mirrors authentic clinical scenarios, making the trained models more generalizable to real-world autism populations and ensuring the predictions align with practical diagnostic expectations. Then the workflow diagram. The workflow begins with data input, AQ10 behavioral scores, and demographic attributes collected for autism screening. Next, pre-processing ensures data quality through cleaning, encoding, and normalization, producing standardized inputs for the models. The modeling phase consists of two distinct pathways: a deep Q network, DQN, inspired neural network that mimics adaptive decision making, and a transformer architecture that captures complex feature interactions and dependencies. Finally, the evaluation phase measured performance across accuracy, recall, precision, and AUC ROC, emphasizing both interpretability and personalization readiness. This end-to-end process reflects a clinically relevant pipeline where AI supports therapists by learning from behavioral data, refining predictions, and eventually generating personalized therapy recommendations that adjust dynamically to each child's evolving behavioral patterns and developmental progress. Then the discussion. The findings demonstrate that both models, the DQN inspired and transformer based architectures, achieved outstanding predictive accuracy, exceeding 99%. The DQN model proved particularly robust in making reliable binary decisions, while the transformer exhibited greater scalability for session-based personalization. Both models maintained minimum training validation gaps, indicating strong generalization and stability. These results align with prior studies in healthcare AI, confirming that advanced neural architectures can deliver clinically dependable predictions. However, limitations remain. The reinforcement learning framework is simulated rather than deployed in real time therapy contexts. Future iterations must include longitudinal therapist child interaction data to validate adaptive feedback mechanisms. Additionally, ethical considerations surrounding data privacy and algorithmic transparency are vital to ensure trustworthy AI implementation in sensitive pediatric healthcare environments. Overall, the discussion highlights significant progress toward dynamic, personalized autism care driven by intelligent systems. Then, about future work and implications. Future work will focus on extending this framework into real time therapy environments where reinforcement learning agents can adapt dynamically to children's behavioral responses. The integration of multimodal data, including EEG signals, speech patterns, and motion tracking, will enhance the system's holistic understanding of each child's needs. Explainable AI components will be prioritized to ensure that clinicians can interpret and trust model recommendations. Beyond detection, this framework aims to support personalized therapy scheduling, progress tracking, and predictive outcome assessment. Importantly, ethical and equality considerations will guide the development of low cost, privacy preserving systems that are accessible to under resourced clinics worldwide. Ultimately, these directions position AI as an ally to therapists, not a replacement, offering scalable, adaptive support for individualized autism interventions in both clinical and educational contexts. Conclusion. In summary, this study demonstrates the artificial intelligence, particularly reinforcement learning and transformer based architectures, can revolutionize autism therapy by making it adaptive, data driven, and individualized. The models achieved exceptional accuracy and stability, showing their potential to function as reliable clinical support system. Reinforcement learning provides the foundation for adaptive decision making, while transformers contribute scalability for longitudinal therapy planning. Together, they represent a promising step toward intelligent, continuously improving care systems. This research moves beyond static diagnosis and into dynamic, responsive intervention design. The ultimate vision is to create autism care that learns and evolves, just as children do. In the words that summarize the mission, towards autism care that learns and adapts like the children it serves. Thank you for your attention.